Okay, so as I go through recording this, I sort of review the footage that I got before. Noticed a couple of errors. So interrupt vector is only 8-bit, it's not 16-bit, so I didn't put in the F register, so let's do that now. Okay, and to set this, so that's the F flag, and we also have another 16-bit value which we're going to put in called AF, which is a merge of the accumulator and the flags register, and this is generally just used to get pushed onto the stack to save the machine state during an interrupt or whatever. But yeah, same procedure, so that's just going to be F and A, F and A, and there we go. Okay, so let's try and do the opcodes now. So I've just gone over some footage and noticed that my keyboard strokes are very, very loud, so I'm going to try and turn that down a little bit and move the keyboard a little further away from the microphone, so hopefully that won't be as loud this time. It's a mechanical keyboard and it is very loud. So okay, let's set up to execute an opcode. Well, this feels really strange because I'm used to really bashing my keys. Anyway, so we need to switch on the opcode. So if we take a look at the first one, so what I'm going to do with these, I'm going to do a few of these. I'm going to go through a few of these at the start, and then I'm going to skip ahead because there are a hell of a lot of them, and the video is already going to be very long. I don't want it to be 10 hours long. So what I'll do is I'll do a few just so that you get the gist of what I'm doing, and then I'll skip ahead, and then I'll just come to I'll show some which are unusual or noteworthy, and we'll come to those, but I'll just skip most of them. So let's just look at move. So the move register basically starts with 0, 1, and then we get 2 register indexes for basically moving one register into another, and we have special values. So remember that register 6 wasn't used, and this is why, because if register 6 is indicated in this index, that means we actually want to use HL, or the contents of the value in the address HL is pointing to. So that's what we need to deal with. But here we can see we've got 3 possibilities. We've got one register to another, we've got the contents of HL into a register, or the contents or a register into the contents of HL. But notice we don't have HL into the contents of HL. That would be pointless. And in fact, that instruction, which would be 0, 1, 1, 1, 0, 1, 1, 0, is not a move at all. It's a completely different instruction. So if we use this range here, we have to make sure we exclude that particular instruction. I believe it's the halt instruction. So let's take a look at what range this is going to be. So if we flip over to binary here, we're going from 0, 1, 0, 0, 0, 0, 0, 0. Okay. 1, 2, 3, 1, 2, 3. So we're going from hex 40 to, and then it will be all ones, so 7 ones. 7F. So from hex 40 to 7F, that's what we need to do in here. So we'll do case int n when n is greater than or equal to hex 40 and n is less than or equal to 7F, and that will be that range. and also we need to exclude the anomalous one, so what that will be 0 1 110 110. So 0 1 110 110, which is 76. So we need to not do 76. So n is not equal to 76, and the rest of them. Okay, set register, and we need the index. So I know this is getting complicated, but the index is of register 1. Okay, so we need to use the mask. So this will be mask 8. Okay, and we're moving 3 bits and opcode. Okay, so that's the register that we're setting, and we're setting it with this one. Okay, so we need to get reg here, so get reg. Okay, and this is register 2, and we're not moving that any bits, so that's going to be mask 8, we don't move that any bits, opcode. Okay, and that should deal with the move. Now, of course, we also have to deal with this, right? When it's the contents of HL, and that's when it's 6. So if we look at get reg and set reg, okay, let's make this, we'll have to take the Pragma out now. So if I is equal to 6, okay, then what we're actually doing is the contents of HL. So instead of returning the actual register, we need to return read byte of HL. Sorry, read mem. Can't remember my own code here. Okay, otherwise we just return the register. Okay, and similarly with set reg, we need to check if I is 6. If it is, write mem HL value. Otherwise we set the register to that value, and write mem will bit trim for us, so we don't need to worry about that. Okay, so what we've essentially done there, if we look here, that is a whole ton of that's 63 opcodes we've just implemented in one go, so that's not bad going. So let's take a look at MVI here, move intermediate, or move immediate. Alright, so the bit mask is here in bits 3, 4 and 5. So the range that we're going to have here is bit 2, which is 1, and bit 3, which is 1, so that's 2 plus 4, so 6. Right, so if we AND the opcode with 6 and the result is 6, that means it's one of these instructions here. So no, wrong. You don't OR it with 6, you need another bit mask. You need to make it 1 for every bit that you're checking, not just the bits that are 1 in the opcode. I do notice it later, however, so don't worry. That's int n when n and 6 equals 6. Now this is move, and this is MVI. So what's MVI do? Oh, okay, so it gets the next byte from the program counter and it moves it into the register. So the register is 3, okay. So it sets a register, so set reg, and this is going to be mask 3, opcode, and we're setting it with the next data value, which is going to be next byte. And yet another error. You'll notice there I used mask 16, not mask 8. Now I'm going to make a load of errors all the way through this video. I do eventually notice most of them, so don't get triggered. And there you go. And that should also deal with this next instruction as well, because it'll move it into the contents of HL, and we've already dealt with that. So it's an immediate instruction, so it looks like it reads the next 2 bytes from the program counter and shoves them into whichever register is indicated by PP. So in this instance it's 1. Okay, so it's if the opcode and 1 is equal to 1. Okay, so case int n. Okay, so what we're going to do, we've got to grab the next word and shove it into that register. Okay, so what's our set reg pair? Okay, so set reg pair, and then the index, that's going to be mask 16. And how many bits are we going back? 1, 2, 3, 4 bits. So 4 opcode, and then we're grabbing the next 2 bytes to make a word. So that's going to be next word. Okay, that's LXI. Load accumulator direct. Okay, it's address 16. So it looks like the contents of the memory location from the next 2. Okay, right. That's moved into A. So that is 111010, code 3A. Okay, so that's a simple case. 3A. Make sure I get this right. We need to read the next word, then we need to read the byte at that address and put it into A. Okay, we'll just use A here. So this is read mem, and we're reading the mem of the next word. Okay, so that's the inverse of this. It takes A and it shoves it in that. Okay, case 32, and that's STA. That's going to be write word, and it's going to be the address of the next word. Sorry, it's write byte. This gets really confusing. Okay, write byte, next word with the value of A. It's not write byte, it's write mem. God damn it. Okay. Alright, we've done a few opcodes now, up to STA. Okay, a few changes. I've changed these to read byte and write byte. You son of a bitch. Okay, a few changes. I've changed these to read byte and write byte. It made more sense than read mem and write mem. I don't know why I did that. But anyway, that's changed. There was an error as well that I made in the last segment. This here I put mask 16, it should have been mask 8. So corrected that. I may have made other errors, but if I spot them I will point them out. So please don't shout at your screen if you spot them before me. Okay, I ran into immediately another issue in this document, and that is, look here, we've just done STA, right? So I looked at the next instruction and it's exactly the same opcode. Yeah, look at the bits. They're exactly the same. So I thought that can't be right. That must be some... Fucking hell. So I'm thinking that's some copy-paste pillock has screwed that up. So I went and I found this document. I'll just make it a bit bigger here. And found that that instruction is actually 2A. So yeah. But this document also has the clock cycles as well for each instruction, and that's actually useful. I'm going to need to know those, because if I want to emulate the speed of the system properly, I need to keep track of the amount of clock cycles that each instruction is supposed to take. So I'm going to be utilizing data from this chart as well, and I'm also going to have to be cross-referencing it because I don't trust this anymore. Right, so we've got down to this point, and now we're on to arithmetical. We've done everything up to that point, and now we're on to arithmetical instructions. These are a bit more complex because they start messing around with the flags. But I've also implemented a clock counter. So from this data here that we got previously, where it gives you all the clock cycles, I made a table of all 256 opcycle times, and they just get added depending on the opcode that gets passed into execute, and that will allow me to keep track of how long the emulator should be taking for each instruction, because the emulator itself is going to be a lot faster than the original machine, so we've got to sort of keep track of how long it's taking to how long it should be taking, and then once it gets ahead of itself enough, you can then pause and yield the thread so that the CPU doesn't race and all that sort of stuff. But that's important in order to keep the speed somewhat realistic. So yeah. So we're up to the arithmetic instructions, so I'm going to have a read through that because it's like I said, it's more complex because of the flags, carry flags and all that sort of nonsense. So many of these operations down here set all of these flags. So let's first deal with the easier ones, which are 0, signed and parity. Now these are all set on the A register, so we can do a simple function for that. So private set Z is if it's 0, so the Z flag is going to be equal to A equals 0. We're going to have to set it with the lowercase version. There we go. The sign flag, that's going to be if is going to be A and 128, so that's the last bit. So if the last bit of A is set, it will stay set after being ANDed with 128, and that will set SF to true because we're using the uppercase version of SF. Parity. Parity is a little bit more tricky. So one way to do parity, if we look here, see what it needs. Okay, set to 1 has an even number of bits, so that's even parity. Okay, so what we can do is we can give a temporary value, so let's say x equals A. Then we can say x or equals x shift right by 1 bit. Then we do that again with 2 bits, and we do it again with 4 bits, and then we set the parity flag to be x and 1. So once you've done all this XORing and shifting, bit 1 of what you've left with represents your parity. So that sets the Z, S and P, and we can just call that at the end of each operation. Okay, so let's add a helper method for this. So this is what we're going to use to add things. So we're going to pass in a value and the value gets added to A. Okay, this is also going to return the result of the addition. We're not going to directly set A in this method. Okay, that's important. You'll see why later on. And we're also going to pass in a carry bit. Now that carry bit is useful because if you're doing calculations, say with multiple bytes, say you're trying to calculate a 32-bit value, you have to manipulate 4 bytes in order to do that. And being able to add with that carry bit is very useful for carrying from one byte to the next. So you can pass that in as 1 or 0, obviously. And what it does is it just ends up adding an extra 1 to whatever you just calculated. So in this instance, we're going to say we're going to make a temporary value. So x is equal to the A register plus the value that we've passed in plus the carry bit that we pass in as well. And I've used the uppercase CY just to make it a little bit more clear that that's a Boolean value that we're passing in. Okay, and then eventually we're going to return that value. So that's the result of the addition. So we can just call ZSP, and I've just noticed that that's not going to work. So we'll pass in a value here actually, int I. Okay. So I. Actually, we don't need to do this now at all, do we? Because we can destroy I. So it's a okay, there we go, that's better. And we can now call set ZSP on the value that we got, which is X. Okay, that's better. Right, now we need to set the carry flag. So the carry flag is going to be if the value of X, okay, is greater than 255. Okay, the carry flag is going to be set. Now, the other flag, the auxiliary carry or the half flag, that's a little bit more tricky. So let me try and explain this a little better. So let's say this is the addition that we're performing. The value of A is 53. The value that we're passing in is 1A, and our carry bit is 1. So we have A plus 3, so it's A, B, C, D, plus 1 is E. Okay. So that column we get an E, and 5 plus 1 is 6. So the answer to that is 6E. Now, let's say that this value isn't a 3, that this value is a 6. Okay. So now we have 6, A plus 6, well that's A, B, C, D, E, F, 0. Okay. Plus 1 is 11 hex. So what we do there is we put a 1 in here and then we carry 1 to the next column. So that's going to be 6 plus 1 plus carry is 7. So the answer to that is 71 hex. Now because we carried from this column to that column, the auxiliary carry bit is going to be set. That's what determines whether you set the auxiliary carry bit, the HF bit, or not. So essentially what we can do is we can add up all of the least significant nibbles of all these things and see if that ends up with a value greater than 15. That's the kind of easy way of doing it. So the easiest way of doing this is HF, probably not the most efficient, but if we take X, okay, and we AND that with F, then we add that with A, which is also ANDed with F, and then add the carry flag, or carry bit I should say. Right, now if all of that is greater than 15, then that flag is set. Okay, so like I say, that's probably not the most efficient way of doing it because we're doing this addition twice, but you know, shouldn't really make that much difference. But it is the easiest and most intuitive way of setting it, I think, so we're going to leave it at that. I've just noticed an error that I've made with my bit logic here. This is wrong, so let's go back up here and see what I did wrong. So with MVI, I'm ANDing it with 6, that's wrong. What I need to do, okay, I need to AND it with a mask of the bits that I need to check. So that's going to be 1 1 0 0 0 1 1 1. Don't know why I brain farted like that, but there we go. So let's see what that is. 1 1 0 0 0 1 1 1. Doesn't matter about these because we're doing it in a range. So what I need to AND it with is 6 7, not 6. Sorry, what did I say there? C7, yeah. Okay, so MVI is ANDed with C7. And similarly, when we did it with here, LXI, I'll look at LXI. Yep. It's not 1. What I need there is 1 1 0 0 1 1 1 1. So 1 1 0 0 1 1 1 1. That needs to be CF. Okay, so that's ANDed with 0x CF. Okay, that's better. Okay, that should work now. Yeah, don't know how I missed that. So let's get back to the adding now.